Hello and welcome to the third part of Lesson 4. In the previous part of this lesson, we looked briefly at various ways that a rheological fingerprint from a material could be built up. We discussed using experimental data for the linear and non-linear viscoelastic regions of a polymer melt, along with data from extensional rheometry. Now, this does assume that the experiments that we want to do are tractable. Not only do we need the right equipment to take the measurements, but we also need the right expertise to use it and to determine when data is likely to be valid or not. Now, we've come across problems involving the validity of rheological data in another course, but perhaps it might be a good idea to start this section of Lesson 4 by reminding ourselves of some of the experimental challenges we can face when dealing with experimental rheometry data. So, I'm going to talk a little bit to start with about the reliability of steady shear data. This data is steady shear data as taken within a rotational rheometer, for example a parallel plate rheometer, where we're constantly rotating one of the plates, rotating it at probably increasing rotational rate, such that we can get a measure of stress and hence viscosity. Now, in lesson 15 of the rheology course, EPD650, I talked around a graph very similar to this, where we have stress as a function of shear rate, and where we have some rather peculiar behaviour going on. And the crux of the conversation that was had in that course was that, look, there are regions of validity where we can believe the data, and there are regions of invalidity where the data that is obtained is completely inaccurate because something's happened to the sample within the rheometer. And typically, under steady shear, polymer melts will sort of distort and fracture and basically be lost out of the sides of the geometry that they're being rotated in. And so you end up with a lack of containment, and you end up not getting valid data beyond a certain critical shear rate. So this can be problematic, because if all we've got in a laboratory that we're characterizing our materials with is a limited range of equipment, maybe we've got a rotational rheometer, how do we actually get the most out of these tools in order to get a fuller picture of the behaviour of a polymer? So what we find is that sometimes it's invaluable to be able to infer steady shear properties from other measurements that may be more reliable within the tooling that we've got. I emphasise the word infer because the types of inference I'm going to be talking about are empirical in nature. They apply to a lot of polymer systems, but not all polymer systems. So these inferences need to be made with your eyes wide open and with a little bit of background research in the extensive literature that is underpinning this kind of practice. So one of the estimating techniques we use is called the Cox-Merz rule. And this is very useful because what it does is allows us to gain an estimate of the steady shear viscosity of a material from complex viscosity data. And if you remember how we got measurements of complex viscosity, it was when we were looking at the linear viscoelastic response of a material under oscillatory conditions. And so we had a sample between our parallel plates being oscillated from low frequency to high frequency, and so you don't have containment problems. And then we got our G prime, our G double prime, and our complex viscosity eta star measurements from those data. And the Cox-Merz rule allows us to say, well, for some polymers, typically linear polymers, the steady shear viscosity as a function of shear rate numerically can overlay the complex viscosity as a function of angular frequency for equal numerical values of complex viscosity and shear rate. Now that's a bit of a mouthful, so it's better explained pictorially. So I'm going to put a graph on my whiteboard here of two different measures of viscosity. The green crosses are those steady shear data that we looked at a minute ago, where we have containment problems. It's well behaved at low shear rate, but then something goes all awry and the data's all over the place, probably because the sample's liberally scattered over the inside of the rheometer. The purple circles are the complex viscosity data. And on the x-axis, what I have are values of either shear rate or angular frequency. But if I'm looking at complex viscosity, I'm looking at angular frequency. Let's say I'm looking at 10 radians a second. That would infer the steady shear viscosity at 10 reciprocal second shear rate. And so we can see the complex viscosity data there at low shear rate and at low angular frequency overlay the steady shear viscosity, which is great. And then when we start to get those deviations in steady shear viscosity due to sample containment problems, our complex viscosity data keeps going quite nicely. And so what this would allow us to do would be to fit a generalized Newtonian model far more readily to our rheology data that we've got. We acknowledge that we're using the Cox-Merz rule to do it. We further acknowledge that we think the material will apply to a Cox-Merz because, for example, it might be linear low-density polythene. It's a linear polymer. But then that gives us a little bit more insight to work with. And again, the thing I've been saying all along is always be aware of the problem you're trying to solve and the accuracy to which you know the answer. And so it may well be that this gives you more than enough accuracy in terms of characterizing material for the problem that you're trying to solve. Now, the Cox-Merz rule isn't on its own when it comes to these kind of empirical relationships that allow you to infer one property from another property. We can do the same with the first normal stress difference. Now, I think this is Laun's rule, and this is empirical again, but it's been tested with high-density polythene, low-density polythene, polypropylene, polystyrene, and a whole host of other petroleum-based thermoplastics. And what we find in Laun's rule is that our first normal stress difference, N1, is a function of our elastic moduli. And again, when we think about how we measure the first normal stress difference, it's within a steady shear experiment. It's a function of the thrust on your Conan plate, or it's a function of your thrust on your parallel plates, but it's mixed in with the second normal stress difference in that case. Hard experiments to do accurately, hard experiments to do at high shear rate, because of course you've got the sample containment problems that we've just talked about. The complex moduli, however, your viscous modulus and your elastic modulus, you can measure at high angular frequency relatively readily and relatively reliably. And so Laun's rule there will allow us to estimate N1 as a function of G' and G double prime. Why might that be useful? Well, if you think back to when we were talking about extradate swell and Tanner's relationship to allow us to estimate extradate swell involves N1. And so if we can characterize N1 as a function of shear rate gamma dot via Laun's rule, which gives us G' and G double prime as a function of omega, then we may well be able to make some sufficiently good estimates of extrusion deformation based on that information. Again, it's all about knowing the problem that you're trying to solve and the accuracy to which you need to know the answer. Okay, so we've talked about material properties. I'd like to very briefly address 2 points, which was how does molecular weight affect material property and how does polymer structure affect material properties. And so let's start with the first, which is the effect of molecular weight on, let's say, the shear viscosity of a material. Now, the first thing we have to do is to define exactly what we mean by molecular weight. So let me put some information on the whiteboard. The graph that I've put there is plotting the percentage concentration of polymer chains for a given molecular weight. And so this is why, if we use the phrase molecular weight, we have to be rather specific, because what we have in reality is a molecular weight distribution. We've got short chains, we've got long chains, and we've got some chains in the middle. And so there are a number of measures that we can apply to a distribution of molecular weights in order to give us some numbers to work with. We can talk about the number average molecular weight, or we can talk about the weight average molecular weight. So whenever you're dealing with properties or with expressions that involve molecular weight, always ask very keenly, well, which molecular weight are we actually talking about here? Now, we can use both of these measures of molecular weight to get an idea of the shape of the distribution. So there is a parameter called polydispersity, which gives you an idea of how broad this molecular weight distribution is, which is simply the ratio of the weight average to the number average molecular weight. Okay, so now that we've honed up our definition of molecular weight, let's see how it might affect a property such as steady shear viscosity. So on this graph, what I'm plotting is the base 10 logarithm of my apparent viscosity, eta, versus the base 10 logarithm of the weight average molecular weight. And so What we see over one range of molecular weight is that the steady shear viscosity is proportional to the molecular weight. Okay, so an increase in molecular weight results in that same linear increase in viscosity. Fine, okay. That's up until a critical value of our molecular weight, after which we see a completely different type of relationship. We see that there's a power law relationship, and in this case typically that power is about 3.4. That critical molecular weight can be found in the literature for selected polymers. It's experimentally derived, so if you can find an MC for the polymer that you're using, it's also a very good indicator that this kind of trend is likely to be observed. So that's one bit of an effect that molecular weight can have. But now what about structure? Because we saw in the previous part of this lesson that actually the amount of chain branching that you get on a structure can really significantly affect the rheological response of that material. We saw it in terms of the extension rheometry of low-density polyethylene versus an extension rheometry of linear low-density polyethylene. So we need to also think about not only the molecular weight overall of the polymer chain, but also the degree of chain branching that those polymers have. And again, keeping in the context of our steady shear viscosity, e to 0, there is a relationship that allows you to, again, estimate its relationship with the degree of chain branching that you have. And so here A and B are material constants. MB is the molecular weight between the chain branches, and mcoon is the molecular weight of the Coon segments of the chain. And if these concepts are unfamiliar, please have a look back at the material from 640 that explains around Coon segments and a bit of molecular theory. So let's draw some summary points here. Sometimes what we might find is that the data that we need to do something cannot be easily obtained using the equipment that we've got. In an ideal world, we'd have access to all sorts of different types of rheometers, and so we'd be able to do all sorts of different types of experiments to get a full experimental characterization. The reality is very rarely that. So sometimes we need to be able to estimate material properties from different types of measurement. And we've seen the Cox-Merz rule. That allows us to estimate shear viscosity from complex viscosity being a far easier and more reliable measurement to take for some polymer systems. We've also seen Laun's relationship, which allows us to estimate the first normal stress difference from the viscous and elastic moduli. Very much in brief, we also had a little look at how we might be able to gain insight into the variation of, for example, an apparent viscosity as a function of both molecular weight and molecular structure. And there's data in the literature that you can find that elucidates a little more on this.